Um, Hello everyone, I'm Hiroyasu INOUE. I would like to share my screen. So thank you for inviting me to this great seminar. The title of my talk is a agent-based model on actual supply chain network. So I would like to introduce myself briefly. I am working in University of Hyogo, and I'm also working for Riken. As I will explain later, I am using supercomputer. So that's why I'm working in Riken, because it has a supercomputer Fugaku. And I'm also working for JST. In the past, I was in Northeastern University and Kiel University. That those visits are related to my work, actually. And my topic is a supply chain disruption, compared with a general talk of Corrado. My talk is quite specific. And supply chain disruption, we hear such news almost every day. I think it's because it's surprising. It's really difficult to predict beforehand. For example, in COVID-19 pandemic case, it started from China, Wuhan, and it is famous for automobile industry. And it is understandable Japan and other countries had some supply chain disruption. But in the end, surprisingly, in EU, medical supply was disrupted. I think it's very difficult to predict beforehand when we had the pandemic in Wuhan. So such things happen in supply chain. Supply chain disruption can happen because of various reasons, like pandemic, war, or disasters, or even some minor firms malfunction may can cause a supply chain disruption because of the domino effect through supply chains. And this kind of risk is increasing because products or services become advanced recently, and that means require more inputs. So a lot of firms are involved from all over the world. So, and that means supply chains become longer and more complex recently. When we hear supply chain, the general idea is something like this, the straight line, like it starts from procurement, production, transportation, and the products or services are sold to final consumers. But in reality, supply chain is something like this. It's more complex because B2B connection is like a complex network. And finally, the product or services are sold to final consumers. So if we have some, disruption here, we have a big trouble. Indeed, actual supply chain in Japan is something like this. This figure shows a actual supply chain, and each dot shows a farm, and the color shows industry of the farm. And this figure shows more than 1 million firms and more than 5 million relationship between them. But the relationship between them cannot be drawn, because if we draw that, we cannot see anything from this figure anyway. Importantly, all of them are connected. So, if a farm has some trouble like bankruptcy or whatever, some of them can be propagated or not. So such condition is really difficult to see beforehand. So what we have done is, first, we just look at the network carefully. And we try to grasp the structure of the network. And the first thing is degree distribution. Degree is a number of a link each firm has. So this figure shows a degree distribution. The horizontal axis shows a degree. And the vertical axis shows the cumulative probability and complementary. So it starts from the largest number. It means like, some firm has a more than 10,000 partners here. And we can see the straight line here. It means a power distribution the degree distribution has. And these two panels are just a separated figure for the left one, and it's just for a number of clients distribution and number of suppliers distribution. We have the same tendency. Why this power distribution is important? If if the power degree distribution has a power distribution, it is called scale-free network, because there is no typical value for this distribution. Like if we have a random network for scale supply chain network, it has some Poisson distribution. So we should see some bump here, but we don't see. As I said, it's straight line power distribution. If a network has a power distribution, there are so many characteristics for those networks. The typical one, for example, is a short average path length. In this Japanese supply chain, the average path length is 4.8. Maybe you remember it's the number of the firm is more than 1 million, but the average path length between them is only 4.8. It's surprisingly short. That means if a shock happens, that shock can be propagated easily to other firms. And another surprising structure of the supply chain network is a circular component, or we call that as walnut structure. Half of the firms are included into this circular component. Means some firms' clients, and we follow that client relationship. In the end, we come back to the same firm. It is surprising. Half of them are included into such large circular component. This is a one component, so everything is connected as a cycle, not a cycle, numerous cycles. And it is not about a recycling issue. It's like, if a firm produces a bolt and the client firm produces some component, and the another firm produces a machine to produce a bolt, we see some cycles here. So like, because of the B2B connection, this kind of thing happens. And why it is important? There are so many issues related to this, but intuitively we can understand if we have a feedback loop, the behavior can be unstable, right? And such small fluctuation can be enhanced. The typical example is called bullwhip effect, and it is famous in business management or operations research area. So some, for example, stores have some, demand fluctuation from final consumer because of the weekly demand or some trend. So this store doesn't want to lose some opportunity to sell their products or services, right? So they have some margin, and the demand is enhanced in this store toward the demand to supplier. So like if this is a wholesaler, this wholesaler has the same thing, same effect, because this wholesaler doesn't want to lose the opportunity to sell. So this kind of fluctuation tends to be enhanced. So what if we have this kind of circular component? This kind of cycle can be infinitely repeated. So because we are thinking about the dynamics of the supply chain, this kind of thing is important. If we only consider the equilibrium, maybe we don't have such, or maybe we don't see this kind of thing isn't important. But in reality, this is very important, right? So that is what I want to say. So if the supply chain behavior is complex and difficult to predict, our idea is very simple. We just replicate a firm's behavior on that actual supply chain data. So we created a model based on the Henriette, invented by Henriette, and so that we can apply that to actual supply chain data. In this model, we don't have any optimization or no price mechanism. So unlike general equilibrium model, it's just that each firm tries to produce as much as possible. I will explain the detail a little bit. In the initial state, it is natural this focal firm I supplies to client firm and final consumers, and it is just a summation toward the supply to client firms and final consumers. In this case, yes, this is the initial state. And the next step is a demand calculation from this firm I to, for example, supplier J. And this equation has two terms. First term is about a demand based on consumption one step before every time step. This is a discrete simulation, so time simulation. So one step before production. Based on that, the demand is decided. Like, as I said, this is the initial production level of this focal firm at time 0 and the previous time step. So the relative size for that. And this Qij means the initial volume from supplier J to firm I. So this is understandable. And the second term is inventory adjustment. In this model, we have inventory for each supplier. And for example, in this case, a supplier J's inputs has an inventory as Ij here. And there is a target inventory size, like if this N is 5, it means 5 days inventory size is a target inventory size. So if there is a gap between them, the current inventory size and target inventory size, that is adjusted. So this term is inventory adjustment. So every firm decides demand like this. So now that the demand for firm I can also be decided based on the client firms and consumers. In this simulation, we consider the demand from final consumer is a constant only for this simulation for simplicity. And but the demand from the client firms, of course, that can be changed. So now we have a demand for each firm. So now we can decide the supply level for each firm. First, we consider supply capacity. So as a kind of facility issue, normally it is equivalent to a initial state production level 0. However, some of firm in this simulation can have some negative effect, like a disaster or because of the pandemic, and they cannot have enough workers or something like that. So in that case, delta is positive and smaller than initial state. So this is a capacity. And also there is some other constraint is like a inventory issue, right? And this firm, focal firm, produces their product or service based on this inventory. By the way, if the supplier is a service industry, there is no inventory. Anyway, if there is an inventory, we consider that as a relative size to initial input from these suppliers. And the word substitutable here means if the suppliers firms are belonging to the same sector, in this model, we consider those inventory are substitutable. So because of that, we here have a S sector. So we aggregate those sectors inventory. And the inventory size is, of course, a constraint for production of this firm I. And naturally, this focal firm I has multiple suppliers. So the minimal inventory size is a constraint of production. And also, as I said, capacity issue also be considered. And the minimal size is considered as a time step T's, this firm's maximum production capability. And we already have a demand for this firm. So the capacity, capability, and the demand, the minimal term is taken as a time step T's firmized supply. And based on that supply, that products or services are delivered to client firms or consumers. If that is not the service industry, and it's B2B, it has a B2B connection, the inventory of the client firms is renewed based on that delivery and the consumption, because at time step T, as I said, this firm I produces something. So that's it. It's quite simple model. And we run this simulation on the actual supply chain data. First example is a Great East Japan earthquake. As you know, we had a large earthquake in 11 or 12 years ago. And the east side of it is famous for Fukushima nuclear power plant. And the east side of Japan was hit by tsunami and earthquake. So we picked up this issue. And a model has a parameter, of course, parameters, and like a inventory size. Each firm has inventory size, but it is not known, and it is unknown, and also how fast a firm recovers from the direct damage. Of course, it recovers, but we don't know how much the rate is. So we tried a super giant searching space. So that so we need these supercomputers with just a in this calibration we did not use an elegant method. It's like we call grid search, so very rough method. But anyway, we try to find the parameter. And this is the result. The horizontal axis shows day, and the vertical axis shows the GDP, daily GDP. And this trajectory is the best solution of calibration. This pink dot is a estimation of the economic behavior after GEJ 2011. We have a gap here. The latter section, later in the later of the simulation, it looks like good, but there is a gap here. So I will go back to this issue later. And so this is the average, and some standard variation has a kind of wide band here. And this is the average of 30 different trials, and 30 different trials are shown in this figure. And interestingly, there is a second wave or third wave. And why we have this kind of different trajectory? That's because we don't know in the earthquake what firms had what extent of damage. So we used the statistics from white paper, like in earthquake, if a firm has a earthquake damage, by this probability that facility completely destroyed or something like that, we did Monte Carlo simulation with that. So we had different 30, in this case 30 different initial state or initial shocks. So that's why we have different trajectory here. And and this is a temporal and geographic visualization, and immediately after the earthquake, we see even different distant places had shock. So because of the supply chain's short path, as I said, and a lot of firms were involved in our simulation, as we can see. And we did some exercise for this GJ. So suppose we could replicate the earthquake simulation. So we can see the effect of, like in this case, network structure, why actual supply chain matters. And first, this red line is a GJ earthquake actual simulation. And this orange line is a randomly shuffled network. It has the same number of firms and the same number of relationships, but those relationships are completely shuffled. If we have that, as we can see, the shock is highly underestimated in the sense of this economic loss. The cause of that is, of course, the structure is totally different, and random network has a relatively larger average path length, for example. So that takes time to propagate, and if there is a time to propagate, there is a chance to recover more for the damaged firms. So that's why we have less economic loss. And the other one is also interesting, and degree preserved random network is similar. It sounds similar, like random network, but degree preserved means based on the actual network, we preserve the degree itself. The number of partners itself is preserved, but the partner is randomly shuffled. As I told you before, the substitution mechanism, in our model, we have that. So, but if we randomly shuffle, the partner structure is completely destroyed, right? So if we have this gap, we can say, so this is overestimation, we can say the actual supply chain has its own resilience based on the substitution, I guess. So that is an interesting exercise, I think. And another exercise is about we change the substitutability and also the cycle issue. The first one is substitution, and this is a benchmark results, the GJ. And what if we only have one product in the economy? So it's maybe weird, but we see some this kind of literature sometimes. And if we do that, so everything can be substitutable. In that case, there is no shock. There is some shock, but it's almost ignorable. On the other hand, we randomly shuffle the products of the supply chain. So it's similar to degree preserved random network, but we just shuffle the products of the supply chain, and we see the worst results. It's interesting. And also, if there is no substitution at all, we have much worse results compared with benchmark case. So the substitutability is quite important for resilience, and I can say the actual supply chain has its own structure for resilience. And this vertical relationship is showing the cycle issue, and we forcibly eliminate the cycle from the supply chain, actual supply chain, and we have the bottom results. As we can see, of course, that the less loss estimation we have, and importantly, we don't see any this kind of second or third wave shock. This can be, a kind of threat for our economy, but, we don't see any second wave here. So as I told you before, that, cycle structure can be a instability. So it shows that, it's kind of evidence, I think. Now, once we have a simulator for the disasters, earthquake, tsunami in this case, we can apply to any earthquake or tsunami. Unfortunately, we will have another big earthquake in the near future. The probability is more than 60%. It's renewed recently in 20 years. The important thing is a magnitude of earthquake itself is similar to 2011 earthquake, but the economic loss is quite larger than that. This is our estimation. The blue line is a new one. As we can see, the loss is much larger than GJ, and in our estimation, it is 4.5 times larger than GJ in 1 year. This is a geographical and temporal visualization again, and the south part is hit by earthquake and tsunami first, and we can see the color of red is denser than the previous one, and a number of farms are involved. Much more farms are involved. That is because in this south area, like representative one is Toyota in Aichi Prefecture, and also Shizuoka or Kanaga Prefecture, we have a kind of center of manufacturing area. So it means in this earthquake and tsunami, we first have a shock for central manufacturing area of Japan. So because of that, the propagation is large and fast. So yeah, and this is a different topic, and I have told you, and there is a gap here for GJ 2011 earthquake, and because we did not consider the like one reason is we did not consider power outage, like Fukushima nuclear power plant issue, and also we ignore the establishment. We could only use farm level data, and it has a headquarter address. So most of farms are located in Tokyo, the headquarters. So, but if they have a branch in Tohoku area, East area, we cannot consider. We could not consider them. So in this simulation, we employ a new data. It's a government statistics, and it has more than 6 million establishments. So we incorporate these data to simulate it. And we did a new calibration so that we can follow this pink bar. And the red one, maybe we can see improvement in the beginning, but in this case later, but it's not satisfiable. So anyway, this green line is a old simulator. I think there is some limitation only to consider the mean squared errors. Yeah, this is the best solution, but yeah, anyway, it is on the way of improvement. And compared with this old simulator, mean squared errors are 5.65 for this new simulator, and this one green one is 15.4, so it has some improvement, but it's not satisfiable anyway. And the last topic is about the pandemic. We had a first wave in 2020 in April and May. The temporal changes, something like this. And those are the restricted area. We do not have lockdown because of the law. So just government requested farms to close workplaces, staying home and social distancing. So we don't know how much they do. They did some reduction of production. Once we have that, we can simulate anything, but we don't know that. So the idea here is just utilize the empirical data, and it is collected by those people. And what if a farm is under lockdown? This farm will be, reduced the production by this ratio or something. So we utilize that, and this is a simulation results. And this blue line is if in 2020 first wave, Japan had a lockdown, we had this size of loss. However, it is past event, so we estimated the economic loss by using industrial index, and this pink area is the loss for in our estimation, and there is much difference here. So we just what we have done is weaken this international standard of lockdown, and by multiplying the same coefficient for every farm. So we found that 32%, the coefficient is 32%, and that result is equivalent for this pink area. So in other words, we can say the containment of the first wave in Japan was economical in the sense that the farm's reduction is only 32% compared with a lockdown. This is a geographical and temporal visualization, and the importantly, those areas are under restriction, but other areas are affected, of course. And now all of prefectures are under restriction, and some of them are lifted, and again, other regions still have it's still affected because of the other regions are still under restrictions. So I think that is I think it's already time. So I'd like to stop here and thank you for listening.